The deep dive. We take complex information, break it down, and give you the knowledge you need fast. Today we're tackling, well, a real giant, a mathematical Everest, you could say. It's haunted number theorists for, what, over 160 years? One of the huge Millennium Prize problems. The Riemann hypothesis. Now, if you followed this area even a little, you know the stakes are incredibly high. The Riemann hypothesis, RH for short, it really underpins our whole modern grasp on how prime numbers are scattered about. It's like the blueprint for where they show up, proving it. That would fundamentally reshape mathematics. Oh, and net the prover a cool $1 million. But our mission today, it's a bit different. We're not aiming for that elegant formal proof. No, we're leaving the really deep theorem wrestling to the mathematicians already deep in those trenches. Our job is, well, maybe more grounded in the near future, but it could be just as revolutionary. We're going to explore how this massive shift in computation, the quantum computer revolution, might completely change how we test this hypothesis, how we verify it, how we investigate it. Can quantum physics give us evidence so strong? Well, strong enough to essentially confirm or maybe even disprove it.
That's exactly the angle, and it's a really important distinction for you listening. The material we've pulled together for this deep dive, it's strictly focused on the computational side of things. We're looking squarely at the near-future impact. How can these quantum systems help us verify RH? Not about generating a classical proof, no, but about pushing computational math to scales we can barely imagine right now. So yeah, we're steering clear of the purely theoretical stuff, the philosophical angles. We're sticking to what these machines might actually let us calculate and simulate.
Okay, right. Let's unpack that straight away because this core idea is key. We're not just talking about faster silicon chips here, are we?
Not at all.
If quantum computers were simply speedier calculators, well, they wouldn't be getting all this buzz. They work using fundamentally different physical rules. It really is a paradigm shift, isn't it, in how we handle information?
Absolutely. A complete paradigm shift. Think about it like this. The biggest, baddest classical supercomputer on Earth, it still runs on the same basic logic as your phone, processing things step by step, just billions, trillions of times faster. Quantum computers, they play by entirely new rules, governed by, well, fundamentally quantum principles, things like superposition, entanglement, and interference. And these principles, they open up computational pathways that are just flat out impossible for classical machines.
Yeah.
That's why there's so much excitement about tackling huge number theory problems like the Riemann hypothesis with them.
Okay, so let's start right at the beginning. The absolute basic building block. Everything we use now, all our data, it's stored with bits, zeros and ones, simple. But the quantum world uses qubits.
Wow.
What's the fundamental difference there, and why does it give us so much potential power?
The key difference is superposition, a classical bit. It has to be in a definite state. It's a 0 or it's a 1, period. A qubit, though, because it's rooted in quantum mechanics, it can exist in a combination, a superposition, of both 0 and 1 at the same time.
Ugh, the classic analogy, like a light switch that's neither fully on nor fully off, but somewhere in between.
Kind of, yeah. Or maybe like it's being flipped, existing in both possibilities simultaneously until you actually finish the action, until you look.
And the moment we measure it, that superposition collapses. It snaps into just one answer, a 0 or a 1.
Exactly. It collapses into a single classical state. But before that measurement, that simultaneous existence, that superposition, it enables something we call quantum parallelism. Take, say, just 30 qubits, not a huge number.
It seems manageable.
Well, that system can effectively represent and process information across more than 1 billion possible states all at once.
1 billion? With just 30?
Over 1 billion, yeah. And it's not checking them one by one. It's like the calculation is happening across all those possibilities simultaneously. That massive inherent parallelism is the engine. That's what drives the theoretical speed-up everyone talks about in quantum computing.
Okay, so superposition gives us this vast space of simultaneous possibilities. Then there's entanglement. You described it as this intrinsic link. What does that bring to the table computationally?
Entanglement. Yeah, this is where, honestly, all our everyday intuition just breaks down. It's this invisible, intrinsic connection between two or more qubits. Once they're entangled, their fates are linked. Measuring one instantly tells you something about the other, no matter how far apart they are.
That's the spooky action at a distance Einstein talked about, right?
That's the famous phrase, yes. For computation, what it means is the quantum computer can create and manage incredibly complex correlations and patterns within the data it's processing. Relationships that classical systems, well, they just can't track efficiently. It would take them an absurd amount of time and memory. Entanglement allows for this really dense, highly connected information structure. And that's absolutely vital for complex algorithms, especially the kind you need for the deep structural problems in analytic number theory.
Right, so we've got the potential space from superposition and the complex connections from entanglement. But wait, if you're running a calculation across, say, a billion states at once, how do you stop it all from just collapsing into random noise when you measure? How do you make sure you get a useful answer, not just, garbage? What's the steering wheel here?
That's the million-dollar question. And it's the entire art, the core challenge of designing quantum algorithms. The mechanism is interference. Interference is like the engine that manages all those probabilities we talked about. You deliberately design the quantum computation, the sequence of operations, so that all the pathways leading to wrong answers, they cancel each other out. That's destructive interference.
Like noise-canceling headphones.
Exactly like that. You're canceling out the computational noise,
Right.
and simultaneously, you engineer it so all the paths leading to the correct, the meaningful solution, they reinforce each other. They build up constructive interference.
Wow. Okay, so it's not just hoping the right answer pops out.
Right.
You're actively using the physics to push the odds massively towards the answer you want.
That's it precisely. You are actively managing the probability distribution to ensure a meaningful outcome. So when you finally measure the system, yes, the superposition collapses to just one classical answer, 0 or 1. But because you've carefully steered everything with interference, the probability that the system collapses onto the single desired correct answer is incredibly high. Ideally, approaching certainty in a future large-scale fault-tolerant machine.
And the most famous example of this power, the one everyone points to, is Shor's algorithm. Now, I know it doesn't directly calculate Riemann hypothesis zeros, but it really shows what quantum advantage looks like in number theory, which is RH's home turf.
Oh, absolutely. Shor's algorithm was the earthquake. It proved that quantum computers could factor large numbers exponentially faster than any known classical method. And that's huge for two reasons. First, it showed these exponential speedups weren't just theoretical dreams, they were possible for fundamental problems in number theory. Second, think about what the Riemann hypothesis is about. Prime numbers, the zeta function. That's analytic number theory. It relies heavily on things like complex arithmetic, finding periodic patterns. Shor's success strongly suggests this entire field is vulnerable, or maybe amenable, to similar exponential quantum speedups. It proved you could translate these abstract number concepts into quantum circuits that fundamentally change the calculation time.
Okay, so we have the quantum toolkit,
You,
superposition, entanglement, interference, and algorithms like Shor's lighting the path. Now let's bring it back to the main target, the Riemann hypothesis itself. Computationally speaking, what is the goal? And why has it resisted, literally, trillions of hours of classical supercomputing?
right, so the absolute core of the Riemann hypothesis is a statement about where the zeros of the Riemann zeta function lie, specifically the non-trivial zeros. The hypothesis states that all of these important zeros must have a real part exactly equal to 1/2.
The famous critical line.
The critical line, exactly.
Yeah.
And the reason that line is so critical, so to speak, is that if even one zero strayed just a tiny bit off that line, it would completely disrupt the delicate balance that seems to govern how prime numbers are distributed. It would mess up the blueprint.
So computationally, what do mathematicians actually do to test this? What are the key tasks?
There are really three core computational jobs. First, they need to actually compute these zeros, find their locations, especially at incredibly high positions up that critical line. We're talking about zeros with enormous imaginary parts, going higher and higher. Second, they need to verify with extreme precision that the zeros they find really do sit exactly on that 1/2 line, within vanishingly small error margins. And third, they need to analyze the patterns. How are these zeros spaced? Are there correlations between them? They look for structure, anything that might hint towards a formal proof.
Now, we often hear these staggering numbers, trillions of zeros already verified by classical supercomputers. That sounds incredibly convincing, so why isn't that enough? Where's the bottleneck? Why does the classical approach eventually hit a wall?
It hits a wall because of scale, primarily. And crucially, because the difficulty, the computational cost, keeps going up. Yes, verifying trillions is amazing work, but there are infinitely many zeros. And crucially, checking a zero isn't a constant cost job. The methods used, like the famous Olisko-Schoenhag algorithm, they get harder the higher up you look. The complexity scales, roughly polynomially, with the height of the zero you're checking.
Okay, let's dig into that scaling problem a bit more. That sounds like the real crux of the issue for classical methods. What does scales polynomially with height mean in practice? Like for the computer doing the work.
It means the higher you go up that critical line, the bigger the imaginary part of the zero you're interested in. Often come t, the exponentially more computational work you have to do just to maintain the needed accuracy. Think about evaluating the zeta function itself near some enormous height t. To get an answer accurate enough to tell if a zero is really on the line or just incredibly close, you have to compute a rapidly increasing number of terms in these complex mathematical series. It's like calculating this incredibly long oscillating sum.
And the number of terms you need depends on how high t is.
Exactly. The number of terms grows, maybe like the square root or some other power of t, and each term needs high precision arithmetic. So you need enough precision to spot a failure, right? To see if the zero is even a tiny bit off the line. This precision requirement forces the amount of computation to explode. Checking zeros at truly astronomical heights, it just becomes impossible. The number of calculations, the memory needed, it rapidly outstrips even the biggest supercomputers we can build.
We're talking timescales longer than the age of the universe for the next significant steps.
Genuinely, we're hitting regions where checking the next few orders of magnitude classically is just
Yeah.
fundamentally beyond reach. That's the complexity wall. We just can't climb any higher using the old tools.
So it's not just about raw speed. It's this escalating, crushing demand for precision and memory just to evaluate the function accurately way up high on the critical line. We need a completely different way to handle that complexity, which naturally brings us back to quantum mechanics.
Hmm.
All right. So the classical approach hits a scaling wall. Let's look at the quantum strategies being developed to try and break through it. There seem to be three main lines of attack researchers are pursuing right now. Strategy 1 sounds like it's aimed squarely at that verification problem, checking zeros at those previously unreachable heights, using quantum search.
Exactly. This first strategy takes that hunt for high-up zeros and frames it brilliantly as a search problem, a needle in a haystack search. Except, the haystack is infinitely large and the needles are these incredibly precise points, the zeros. We're looking for specific locations in this vast, seemingly unstructured space along the critical line.
And for that kind of unstructured search, the go-to quantum tool is Grover's algorithm, right?
That's the one. Grover's algorithm gives you a quadratic speedup for searching an unstructured list or database. What that means is, if a classical computer needs, say, n steps to check every item in a list of size m.
Which could be astronomical.
Right. Grover's algorithm can potentially find the item in roughly the square root of n steps.
Okay, square root. Now, compared to the exponential speedup of Shor's algorithm for factoring, quadratic maybe sounds less spectacular.
It might sound less dramatic on paper, sure. But when n, the size of your search space, is truly colossal, a quadratic speedup is still completely game-changing. Monumental. Think about it. Imagine your search space has, I don't know, a trillion locations. That's one followed by 24 zeros. Classically, you might need roughly that many steps. Quadratically, you reduce to the square root one, followed by only 12 zeros. Still immense, but potentially feasible, where the original number was simply impossible.
So it brings impossible timescales down to merely enormous ones.
Precisely. That reduction allows us to potentially verify zeros or search for a counterexample at heights that classical methods literally cannot touch, not in billions of years. This search approach is probably the most direct way a quantum computer could find that smoking gun, that one zero off the line that would instantly disprove the whole hypothesis.
Okay, so that's boosting verification speed and reach. Strategy 2 sounds more abstract. It involves massive linear algebra, turning number theory problems into equations.
Yeah, this strategy is really fascinating because it shows how computation bridges different fields. It turns out that many deep properties related to how primes are distributed, or the really intricate behavior of the zeta function. These can often be mathematically rephrased. You can translate them into the language of linear algebra. Things like finding eigenvalues, characteristic values of gigantic matrices, or solving enormous systems of linear equations.
And classically, the matrices you get from these high-level number theory questions are just impossibly huge, too big to handle.
It's exactly. Too large, often too dense, meaning lots of non-zero entries, and just too complex to solve directly within any realistic time frame.
Okay, so where does quantum step in? Is there a quantum way to solve these massive equation systems?
There is. It's called the Haro-Hasidim-Lloyd algorithm, or HHL for short. HHL offers the potential for an exponential speedup in solving systems of linear equations. But, and this is a big but, it only works efficiently under certain specific conditions about the input data.
Ah, the catch. An exponential speedup for solving equations sounds almost too good to be true. What are those conditions? Does it actually help if setting up the problem takes forever, classically?
That is the critical question, absolutely. And it points right at the implementation challenge. AKHL shines mainly if the matrix describing the system is sparse, meaning mostly zeros. Or, alternatively, if the initial quantum state that represents the problem's input vector can be prepared very efficiently, very quickly on the quantum computer.
And how does that square with number theory problems? Are the matrices usually sparse?
Often not. Problems coming from deep mathematical structures, like those tied to the zeta function, frequently translate into dense matrices packed with non-zero numbers. So the real quantum insight here might not be about brute forcing the entire solution to a dense system. Instead, the idea is maybe you formulate a specific property related to the zeta zeros, maybe some subtle statistical behavior, or a hidden correlation you suspect exists as a system of linear equations.
So you're not trying to find every single variable's value in the equations.
Correct. You're aiming for an informational shortcut. The HHL algorithm might be able to extract a key feature of the solution. Maybe it calculates a specific average or finds a dominant characteristic or estimates a statistical property of the solution vector without needing to compute the whole thing explicitly.
I see. So if that extracted feature matches what the Riemann hypothesis predicts it should be?
Then you get incredibly powerful computational evidence supporting the hypothesis. It gives you insight into the structure of the solution, a structure that might be completely inaccessible classically because you could never compute the full solution itself.
It lets you peek at the answer's properties without calculating the whole answer. That's clever.
Very clever.
Mm.
It's about extracting specific insights, providing computational evidence about the truth of the underlying mathematical statement, not just crunching all the numbers.
That ability to probe the abstract structure is really profound. But strategy 3, the quantum simulation approach. You mentioned this earlier. This sounds like the most ambitious, maybe the most mind-bending, trying to find a physical system that behaves like the zeta function.
Right. Here's where it gets really interesting, as you said. This pushes beyond just computation into simulation, into experimental physics territory almost. This whole approach is heavily inspired by a known and frankly quite startling statistical connection. It's the link between the spacing of the zeta function zeros along the critical line and a concept from physics called random matrix theory.
Okay, let's pause there. Random matrix theory, RMT. For listeners who haven't bumped into this, what's the connection? Why is it so suggestive regarding the Riemann hypothesis?
The connection is known as the Montgomery-Odlyzko law. Years ago, Freeman Dyson and Hugh Montgomery were chatting, and they realized something uncanny. If you look at the statistics of the gaps between consecutive zeros high up on the critical line, how far apart they tend to be, that statistical distribution perfectly matches the distribution of eigenvalue spacings in certain types of large random matrices.
The kind physicists use to model complex, chaotic quantum systems?
Exactly those, like the energy levels in heavy atomic nuclei. The match is just too good to be a coincidence. It strongly suggests that the zeta zeros aren't just randomly placed, they behave as if they are the energy levels, the eigenvalues of some underlying undiscovered quantum mechanical system. This led to this profound idea, often linked to something called the Hilbert-Polya conjecture. Maybe there exists some physical quantum operator, some mathematical description of a quantum system, like a Hamiltonian, whose energy levels perfectly match the imaginary parts of the non-trivial zeta zeros.
Wow. So the simulation strategy is forget calculating the zeros abstractly. Let's try to build or at least simulate a physical quantum system whose natural energy levels are those zeros.
That's the dream, precisely. If you could design and then simulate this hypothetical quantum system on a quantum computer, well then proving the Riemann hypothesis that all zeros are on the line might become equivalent to proving some specific physical property about the energy spectrum of that simulated system.
And crucially, simulating such a complex quantum system is exactly what classical computers are terrible at, but quantum computers are naturally suited for.
Bingo. That's a task that scales exponentially badly on classical machines. But a quantum computer could potentially simulate it natively. So by running this simulation, measuring the energy levels of this engineered system, the quantum computer could gather huge amounts of statistical data about how these zeta zeros are spaced out, especially at incredibly high energies corresponding to high up the critical line. If you observe the predicted patterns, particularly the characteristic repulsion between zeros that RMT predicts, holding true at energies far beyond classical reach, that would be extraordinarily strong empirical evidence.
So it wouldn't be a formal proof.
No, not a formal proof, but it would provide mathematicians with an undeniable target. It confirms the deep structure predicted by the hypothesis holds true on a vast scale, giving them confidence and direction for finding that elusive proof.
Okay, we've got the three big quantum strategies mapped out. Grover's search for scaling up verification, HHL for getting at abstract structure via linear algebra, and this fascinating simulation idea linked to random matrix theory. Now let's get a bit more concrete. What specific quantum computational tools or techniques are needed under the hood to make these attacks on the zeta function actually work?
Right. For the more direct computational strategies, especially for actually evaluating the zeta function itself at those large heights t, a couple of tools are really key. First and foremost is the quantum Fourier transform, the QFT.
The QFT. How does that specifically help with the kind of calculations needed for the zeta function?
Well, evaluating the zeta function high up involves calculating these things called exponential sums, or sometimes Dirichlet polynomials. These are complex oscillating sums with many terms. Classically, calculating these sums accurately, especially with the required precision, becomes incredibly resource intensive. It's a big part of that scaling problem. The QFT is powerful here because it's exceptionally good at finding periodicities and analyzing frequency components. It allows quantum algorithms to potentially evaluate these sums much more efficiently than classical methods. The hope is it could reduce the computational cost for evaluating parts of the zeta function calculation from something that scales badly, maybe exponentially classically, down to polynomial scaling on the quantum computer.
That's the kind of complexity shift we need.
Exactly. That's the potential game changer for breaking through the classical bottleneck. A second important tool, related in some ways, is quantum amplitude estimation. Algorithms based on amplitude estimation can allow you to approximate certain numerical values, maybe the value of the zeta function itself, or some component needed to check a zero using significantly fewer computational steps, fewer samples, than classical methods like Monte Carlo might require for the same accuracy.
So it's about getting the answer with less work.
Essentially, yes, more efficient estimation, which is vital when the function you're estimating becomes incredibly complex and expensive to compute directly at high values of t.
Okay, and going back to that statistical simulation approach using random matrix theory, you said QCs can natively simulate these RMT systems. How much better is that than what classical computers do now?
Well, classically, physicists and mathematicians use Monte Carlo simulations to generate large random matrices and study their eigenvalue statistics. But these classical simulations are themselves computationally very demanding. They're limited in the size and complexity of the matrices they can handle effectively. The potential quantum advantage is huge here. A quantum computer is a quantum mechanical system. It operates according to those rules natively. So it could potentially embody or directly simulate the behavior of these random matrix ensembles much more naturally and efficiently. This would allow us to perform statistical tests, checking if the zeta-zero spacings continue to match the RMT predictions at scales, at matrix sizes or energies that are simply unreachable for classical Monte Carlo methods. It would give us immense statistical confirmation, verifying that the Montgomery-Aldisco pattern holds up in regimes we can't currently probe.
Right. So given all this incredible theoretical potential, the speed-ups, the simulation power, the search capabilities, what's the realistic outlook? Let's talk timeline. Next 10, 20 years. And crucially, should we really be expecting a quantum computer to print out QED, Raman hypothesis proven?
Yeah, we absolutely need to manage expectations there. The next decade or two, the goal is definitely not a formal analytical proof spat out by a machine. That kind of reasoning, building logical arguments, that still seems firmly in the realm of human mathematicians. The primary impact, the realistic goal, is going to be in computational and experimental mathematics. First, unprecedented verification, using Grover-like searches to push the boundary of verified zeros to heights that are just astronomical compared to today. Finding even one counterexample there would be earth-shattering.
Instantly disproving RH.
Instantly. The second big impact area is pattern discovery. Using tools like HHL and simulation to uncover subtle correlations, statistical patterns, structural properties related to the zeta function that are currently hidden from us simply because we lack the computational power to see them. This massive trove of empirical data, these newly visible patterns, that's what will guide the human mathematicians. It provides the roadmap, the targets, for building that final rigorous proof.
So it sounds like in the near term, we're looking at hybrid approaches, a real partnership between classical and quantum machines.
Absolutely. That's the most realistic path forward for the next decade, probably longer. Hybrid classical quantum algorithms. Picture this. You have a classical supercomputer doing the main work, managing the overall calculation. But there's one specific part, maybe evaluating a particularly nasty exponential sum, that's the bottleneck. You offload just that incredibly hard piece to a small, specialized quantum coprocessor.
Which uses QFT or something similar to accelerate it.
Exactly. It computes that piece much faster than the classical machine could. Then it hands the result back to the classical computer, which integrates it into the main calculation and handles things like error checking and data management. This way, you leverage the quantum speed up where it matters most, but you minimize the demands on the quantum hardware, which is still pretty noisy and limited in scale.
Okay, that makes sense. But it also leads us right into the limitations. What's actually stopping us from doing this right now? Why aren't quantum computers already churning through zeta function calculations?
The biggest immediate roadblock is definitely the hardware itself. We're currently in what's called the NI-HISQ era, noisy intermediate scale quantum. Intermediate scale means we don't have that many qubits yet, maybe hundreds or a few thousand in the best systems. Noisy means they're prone to errors. Environmental factors, imperfect control, they mess up the delicate quantum states.
And for something like checking RH zeros, you need extreme precision. Errors are fatal.
Utterly fatal. The kind of deep, complex, ultra-precise calculations needed to verify a zero at extreme height t. They require fault tolerance. You need reliable quantum error correction to protect the computation from noise. And building large-scale, fault-tolerant quantum computers, that's still a major engineering challenge. It's likely years, maybe a decade or more away for the scales needed for these really hard problems.
So hardware noise and scale is limitation one. What else?
It's not just the hardware, it's also the software side, the programming challenge. Specifically, something often called the oracle problem.
Mm-hmm.
Many quantum algorithms, like Grover's search or even parts of HHL, they need a component called an oracle. This is basically a quantum subroutine that encodes the problem you're trying to solve.
Like it needs to calculate some number theoretic function quickly within the quantum circuit.
Precisely. For our age, you might need an oracle that efficiently calculates parts of the zeta function, or performs modular arithmetic, or checks some property related to primes. Building these oracles efficiently translating the specific mathematical function you need into an optimal sequence of quantum logic gates can be incredibly complex and resource-intensive in itself. The more complex the math you want the oracle to do, the more qubits and gates it takes, and the more susceptible it is to noise on current machines. So designing efficient oracles is another huge hurdle.
And then there's the final, maybe philosophical limitation we keep coming back to. Even if we overcome the hardware noise, build perfect oracles, and verify RH holds for, say, the first 10 zeros.
It's still not a proof.
Right. It's incredibly strong evidence, but not proof in the mathematical sense.
Exactly. That's the fundamental distinction we have to keep clear. Computational verification, no matter how extensive, only provides empirical evidence. It shows the pattern holds for all the cases checked. A rigorous formal proof the kind mathematicians strive for has to cover all infinitely many cases through logical deduction. That still requires human insight, ingenuity, building that chain of mathematical reasoning. The quantum computer in this whole endeavor is best thought of as an extraordinary new scientific instrument, like an incredibly powerful telescope for exploring the mathematical universe. It lets us see details and structures at scales we could never access before. But it's still the human mathematician who has to interpret those observations and construct the final theory, the final map. #outro. So to wrap things up, the key takeaway here is that quantum computers probably won't hand us a direct proof of the Riemann hypothesis anytime soon. That's not their role. Instead, they promise to completely revolutionize how we investigate it. They're like this amazing new lens on the mathematical world. They enable verification at previously unimaginable scales using tools like quantum search. They let us discover hidden patterns by simulating statistical models like random matrix theory natively. And they offer glimpses into deep structures using advanced linear algebra techniques like HHL. All this computational power will likely generate overwhelming empirical evidence, extending our confidence in the hypothesis far beyond current limits, and, crucially, providing the vital clues and structural insights that human researchers need to finally construct that formal proof.
So what does all this mean for you listening to this? For the person trying to keep up with where science and tech are going? It means that some of the deepest, most abstract questions you can ask questions about the very fabric of numbers, the primes, they're no longer just confined to blackboards and theoretical papers. They're becoming deeply intertwined with experimental physics, with cutting-edge quantum engineering. The line between pure mathematical truth and empirical observational evidence is getting blurrier, more fascinating. We're really watching technology start to probe the foundations of abstract thought itself. Which leaves us with a final, pretty provocative thought to chew on. Imagine a future, maybe a few decades from now. We have large, fault-tolerant quantum computers. They run verified, error-corrected algorithms, and one of these machines verifies that the Riemann hypothesis holds true for zeros up to a height so incredibly vast, so immense, that checking it classically would literally take longer than the entire age of the universe. Would that overwhelming computational evidence be enough? Enough for the world of mathematics, of science, to essentially treat the Riemann hypothesis as if it were proven, even without that traditional human-derived analytical proof. Where does computation end and proof begin? It's a fascinating new frontier for what we consider known, something to think about. Welcome to the deep dive. We take complex